So the next session. Okay. The next section will be about nexus and also consumer consumption and production patterns. So clearly, several of the SDGs are related to the nexus, and that's and to consumption and production patterns, and that's why it also played a prominent role in the SHAPE project. And so we first have two presentations. And the first presentation will be by Vassilis, which will explain the work that is done on SHAPE. Vassilis Daioglou is working at PBL, Netherlands Environmental Assessment Agency, which was originally involved in the project from the Utrecht University partner. And in his presentation, he will present not the work of several model teams. So over to you, Vassilis.
Thank you. Can you see my screen?
Yes, we can.
Excellent. Hello, everybody. My name is Vassilis Daioglou, and I'm going to present to you the implications of the Sustainable Development Pathways on the climate, land, energy, and water nexus. So the provision of human services puts pressures on natural and social systems. So as we can see in this stylized diagram, the energy system may have pressures on the land system by, for instance, if there's an increased demand for biomass, for bioenergy, let's say, this may lead to land use being required to provide that biomass. And in turn, the land system, through increased provision of agricultural products, either for bioenergy, as said, but also providing further food and feed for nourishment, may require further irrigation, thus putting pressures on the water system. And all of these systems, they interact with each other, but they also have bidirectional interaction with climate. So for instance, primarily through greenhouse gas emissions, which leads to anthropogenic climate change, but climate itself may affect energy demand by changing, for instance, heating and cooling loads, but also the productivity of land and the availability of water. So in this project, or in this presentation, I'm going to show how we used the Sustainable Development Pathways to understand what this nexus looks like. So some of the pressures that we're looking at are the pressures on climate. So that is primarily the greenhouse gas emissions that we see, pressures associated to land, and for that we're looking into agricultural demand. The energy pressures are demand for primary and final energy in order to provide energy services. And then finally, for the water system, we're looking at water withdrawals. And these pressures, they have a number of impacts across multiple indicators that are also very relevant for meeting the Sustainable Development Goals. So on climate, that would be temperature change, but also the associated carbon prices to stay in line with strict climate goals. For the energy system, we investigate the implications for energy access and prices. These are intimately related, but also the requirements for investments and infrastructure in the energy system throughout the SDPs. On land, we're looking at land use and the implications for biodiversity and food prices. So also there's an element of access to food there. And then finally for water, looking at drinking water access and quality. Now, how the CLEW nexus behaves and how the pressures and the impacts interact really depends on the context. There may be synergies, they may be trade-offs, but these really depend on the system which governs the pressures and the impacts. So that's why we're looking not only at the Sustainable Development Pathways in this presentation, but I'm also going to compare the results to counterfactual scenarios. So that would be an SSP-2 baseline and an SSP-2 that meets a 1.5 target, where the SSP-2 kind of portrays middle of the road socioeconomic developments without specific focus on meeting sustainable development goals. So this is also in line with what Bjorn presented earlier, where he also contrasted the SDPs with the SSP-2 scenario. So just a quick recap on the SDPs and particularly their relationship with the CLEW nexus. We have the economic-driven innovation scenario, so SDP-EI, which is a market-driven transition. Technologically, it focuses a lot on electrification and focusing on technological solutions. It has some dietary shifts, and there's an active sense of carbon management, where carbon is priced and it's treated as a resource and in order to meet certain climate goals. Then you have the managing the global commons, which the transition is largely dictated through regulation with a focus on human services. while it does have obviously some technological advances, it focuses mostly on efficiency. So efficient behavioral and efficient technologies. And thus there are some dietary shifts which may affect the land system. And there's some sense of carbon management. And then finally, there's the resilient communities, the RC scenario. This is a post-growth society that is really dictated by low consumption and low waste lifestyles. And thus it also has, for instance, very rapid dietary shifts. And particularly meeting climate goals depends much more from a demand side rather than a supply side. So there's reduced sense of carbon management here. So quickly jumping in to some of the quantitative results, I'm going to first show a couple of slides with the pressures across the CLEW nexus. And before jumping into some of the results, I want to guide you a little bit through this slide because a lot of them are going to follow this format. I'm showing the results for a single model for the sake of brevity, but the results in detail are shown for a single model, but you can see the second model, in this case, the Remind Magpie, in the form of the black dots. And then I'm showing the results for 5 scenarios. First, the SSP2 baseline, then an SSP2 that meets strict climate targets, and then the 3 SDPs, which also meet the 1.5 degree target. So what we see here is the final energy demand across all scenarios broken up across demand sectors. And first thing that we see on the SSP2 baseline is with no extra actions according to current developments, we expect final energy demand to increase significantly, driven by increased consumption, largely also increased welfare, and such things which drive increased energy demand. While for the SSP2 1.5 degree scenario, where we meet climate targets, there is a reduction in energy demand driven by the required carbon prices. However, looking into the SDPs, first focusing on the economic innovation, we noticed that in the short term, there is a little bit of an increase in energy demand, but really quite minor. But in the long term, it does decrease. And this is because the increased electrification and the use of high-tech technologies really mitigates the need for high final energy use. And this is further seen in the MC scenario, where in this case, it's efficient technologies and efficient behaviors, which lead again to a overall decrease in energy demand compared to today. And then really the extreme scenario, the lifestyle post-growth change scenario, where complete change in behaviors and then the demand for energy services, demand for industrial products, demand for transport leads to a very low energy demand. However, this is important to keep in mind, and as mentioned also before, this is going to be talked more about in a presentation by Jarmo Kikstra later. All of these scenarios do meet decent living energy standards for all of the global population. So we have cross-checked these energy demands to make sure that really fundamental energy needs are met. And another thing that we see is if you compare the bars with the black dots, that there is overall consistency in the models concerning the final energy demand projections. The exact numbers are different, but the models do portray the same dynamics. Now, what does this mean concerning primary energy demand? Here we see again for all the scenarios and for the Remind model in this case, the demand for primary energy across different primary energy carriers. And while in the SSP2 baseline, you do have obviously an increase in primary energy demand driven by the increase in final energy demand. We do see quite a high use of fossil fuels. In all of the scenarios that meet climate targets, these are very rapidly phased out, particularly in the SDPs. Very rapidly, we see wind, solar, and to a lesser extent, modern biomass making up the majority of our primary energy supply. So this shows a complete transformation of our energy systems. Another thing I want you to focus on are the green bars. So this is the use of modern biomass. While the SSP2 1.5 scenario depends quite a bit on modern biomass, making say 10 to 20% of total primary energy supply, in the SDPs, it's present, but it plays a much more minor role. And this is partly because the lower overall pressure for energy demand, lower energy demand needs, means that it's easier to decarbonize our energy systems with renewables such as wind and solar. And fundamentally, there's also a lower need for biomass combined with carbon capture and storage. There's a lower need for CDR, and I'm going to talk about that a little bit more later. So we do still see some biomass being used, but it primarily comes from residue streams without the need of energy crops. There's a very limited use of nuclear power. It actually doesn't even show up in these graphs. And once again, we do see consistent patterns across the models. So moving on to agricultural demand, both the SSP2 counterfactuals, the baseline and the mitigation scenario, they see an increase in the requirement for agricultural products. In the SSP2 baseline, it's mostly just food and feed, and to a lesser extent livestock, while in the SSP2 1.5, we see that purple bar really exploding. So this is the need for energy crops to provide bioenergy, as also shown in the previous slide. And this is bioenergy to meet the increasing energy demand, but also in principle to provide negative emissions in the form of bioenergy with carbon capture and storage. Both of these are needed to a much, much lesser extent in all of the SDPs, where in fact we see for the SDP-MC and SDP-RC an overall decrease in the requirement of agricultural production, driven both by lower levels of energy crops compared to the SSP2, but also overall lower levels of food and feed demand and livestock demand. This is obviously driven by the different dietary patterns that we see, especially in the MC and RC scenario. The SDP-EI has the higher agricultural demand for all the SDPs, but still because of very high efficiencies, it's generally lower than SSP2. So immediately we see how we avoid a certain nexus trade-off here. In the SSP2, meeting climate targets leads to very high use of energy crops, which leads to very high agricultural demand. While in the SDPs, this lower requirement for energy, this lower requirement for CDR means that agricultural production doesn't have to go quite as high for the provision of energy crops. Now, what does this agricultural demand mean concerning land cover change? Here we see for all the scenarios, the indexed land cover change for food crops and pasture, that's the red and more salmon colored lines. And then for natural areas, mostly forest and other natural lines, those are the green lines. And basically what I want you to focus on is how in the SDPs, the green lines go up and the reddish lines go down. So the requirement of managed land and agricultural land is really decreased in all the SDPs, while the availability of forests and other natural lands increases across all the SDPs, with the pattern being most pronounced in SDP, MC, and RC, which have these very strict dietary shifts. This contrasts with SSP2, which has a huge increase in food cropland, but also the SSP2 1.5, which while it's a bit more benign than the SSP2 baseline, it still is quite problematic. So moving on to the next aspect of the CLEW nexus concerning water withdrawals, here we see the results of the image model. So while in the SSP2 baseline and 1.5 scenario, we see an overall increase in water withdrawals, driven primarily by irrigation, but also to a lesser extent by increased water use in industry as industrial production increases. In all of the SDPs, we see that water withdrawals are mitigated to a very large extent. So according to the image model, this is largely because of lower requirements for irrigation. This is also combined by lower requirements for bioenergy and the changes in diets, which leads to lower agricultural production, but also lower needs from industrial production and electricity generation. And this is because of efficiency gains. It's also because of, especially in the RC and MC, the lifestyle changes which lead to lower requirement for industrial output, but also for the electricity generation, the less dependence on thermal power plants, since the energy systems, they're almost completely shift to variable renewables. And while both models show that the water withdrawals are mitigated in the SDPs, interestingly enough, they disagree a little bit on what drives the decrease. So in the Remind model, which we see a bit of a sharper decrease in water withdrawals, that is almost completely from irrigation. So we see a little bit part of the structural uncertainty in the models on how they model water withdrawals here. So then moving on to the pressures from emissions, here we see the total greenhouse gas emissions across a number of emission sources for all the scenarios. And as expected, both the SSP2 1.5 and all the SDPs have very rapid reductions of greenhouse gas emissions in line with meeting strict climate targets. One thing that I quickly want to focus on is if you look at the SDP-RC, the emissions from non-CO2 gases, so that's that salmon area and the yellow area for methane and nitrous oxide respectively, is quite low compared to the other scenarios. This is because the dietary shifts implied in the RC make it easier to mitigate non-CO2 emissions, which makes it overall easier to meet climate targets. And another thing that is true for the SDPs compared to the SSP2 is the lower requirement for overall net negative emissions. So this is zooming in to that previous graph, but focusing only on the net negative aspects. So we see here the results for image, where we see the SSP2 has quite a high dependence on net negative emissions coming both from land use, in this case afforestation, but also energy use in the form of bioenergy with carbon capture and storage. Both of these are required to a lesser extent in the SDPs, particularly the MC and RC, where it becomes easier to meet climate targets, but still image does depend to quite a significant extent on net negative emissions in order to counteract certain hard to abate sectors, which are still projected to have certain positive emissions throughout the projection period. And another thing that we notice here is quite a disagreement across the models. So it's important to note at this point that image is a model that has a little bit of inertia and a little bit of difficulty in completely transitioning some systems compared to the Remind Magpie model. So image is generally a model that depends a little bit more on net negative emissions, while we see the Remind Magpie model has a much lower requirement. The black dots have a lower requirement of net negative emissions. And this is also reflected in this figure, which shows total carbon capture and storage across all scenarios. It's 0 in the baseline because there's no climate policy there. It's very high in the SSP2 scenario, driven largely by bioenergy with carbon capture and storage, which contributes to net negative emissions, but also a continued use of fossils with carbon capture and storage in the SSP2. For the SDPs, we see that the combination of fossils with CCS is initially a bit high, but decreases over time as the energy system can continue its transition towards cleaner energy carriers. But there still is some bioenergy with CCS in order to contribute to this carbon dioxide removal and this requirement of net negative emissions. And another thing that we see is that the use of direct air capture is, even though we allowed it in the SDPs, or we allowed it in the SDP, EI, and MC, it isn't used that much. Basically, the carbon prices never go high enough to make this technology really worthwhile, only in the EI scenario towards the end of the century. And again, you see the significant disagreement between the models because of their structural differences and how they project decarbonization strategies. So these were the pressures from the CLEW nexus. And now I want to look at some of the impacts. So how do these pressures affect certain physical and social indicators? So first, focusing on climate, here we see the development of the carbon prices for all the scenarios, and I show the results in the form of ranges, where the ranges are basically the ranges across the two models. So the first thing that we see is that concerning carbon prices, for the SSP2 baseline, that's the black dot, it's obviously 0. But for the SSP2 1.5 scenario, that's that reddish line, we see the carbon prices rapidly increase to very high levels. While for the SDPs, they generally are lower than the SSP2 1.5. And this is simply because these scenarios have higher technological changes, they've improved governance, they have certain policies actively focusing on reducing emissions, and there's lower pressures. There's the effort needed to meet strict climate targets is lower, and that's particularly shown in the SDP-RC, which has quite low requirements for carbon prices in order to meet climate targets. So moving into the impacts on the energy system, here we see the energy investments, the population using solid fuels, and the price of electricity index. So first, looking at the energy investments, looking at the red line, so the SSP2 1.5, these are projected to be very high in the SSP2 1.5 scenario. The energy investments are projected to be very high, driven largely by the very high need for carbon capture and storage, but also the overall increase in energy demand. Now, this increase in energy demand also leads to a reasonably high investments for SDPEI, especially when we compare it to the MC and RC scenarios, which have quite low energy investments since they have a lower dependence on CCS and overall lower energy demand. So overall, it becomes easier, cheaper to meet all the targets. For population using solid fuels, all of the SDPs meet certain access and clean fuel goals. We only show the results for the image model here. But what I want to quickly point out is a certain trade-off that exists in the SSPs. So you see the black dot, that's the SSP2 baseline, is generally lower than the red dot. So in the SSP2 case, when you try to meet climate targets, certain poor households are priced out of access to modern fuels. So we see a trade-off with climate policy there. When you apply climate policy, population using solid fuels increases in the SSPs. In the SDPs, we've avoided this because there's overall lower pressures, overall energy prices, and we have ancillary policies included in the models that ensure access to energy. And this price effect is also shown in the last panel where we see the price of electricity, where in the SDPs, we see that the ranges of projected electricity prices are generally lower than the SSPs. In one of the models, in fact, electricity becomes even cheaper than today, even though we have a completely decarbonized electricity system. Moving on to land, there's a certain narrative coming up here that I want to walk you through. First, we see that food demand, it increases in the SSPs and also in the SDPEI, since we don't have very significant dietary shifts there. But generally, we see that the RC and MC scenarios, so the managing the global commons and the resilient communities, they have quite low food demand projected by both models. This lower food demand and lower requirement for agricultural production, also driven by reduced waste, that's actually largely what reduces the food demand here, leads to a lower requirement for yield improvements. There's lower pressure on agricultural production to increase yields due to increased food demand. And that's why, again, we see the MC and RC scenarios do not see massive increases in cereal yield. And this has a certain knock-on effect on the requirement for fertilizer use, where, again, the RC and MC scenarios have fairly low fertilizer use. And then finally, we also see these dynamics reflecting in the food price, where all the SDPs, but particularly the MC and RC scenarios, have very low food price indices. While we see the exact opposite in the SSP2 1.5, where cereal yields have to increase a lot, fertilizer use increases a lot, and food prices increase a lot, largely driven by rather poor diets, but also quite high levels of waste. And these higher food prices also imply that food insecurity is also higher in the SSP2 1.5. So another trade-off with climate policy, which is avoided in the SDPs. And this is further reflected in the availability of natural land. As also discussed earlier, it's higher in the SDPs because you have this lower pressure for agricultural products. The availability for natural lands can be higher, which has a knock-on effect on biodiversity intactness, where we see for the SDPs, once again, they perform better than the SSPs because of these lower pressures on land use driven by changing diets, but also the changing energy system and lower need for biomass and bioenergy to help the decarbonization efforts there. So stepping back a little bit after this very rapid barrage of results, what exactly do we see? The SDPs fundamentally reduce trade-offs and increase synergies. So the reduction of energy, material, and land demands reduces certain pressures. So for instance, we saw that lower need for agricultural area, lower need for agricultural products allows us to have higher natural land cover. And there's also associated implications for fertilizer, water, energy needs, and biodiversity. And similarly, we can see also in the energy system, these lower pressures imply that it's easier to decarbonize the energy system. It's easier to provide adequate energy to everybody, and it's easier to meet climate targets with a lower need for investments at a faster rate and at lower overall requirements for carbon prices. So yeah, generally it is easier to decarbonize, and fundamentally it also means that there's a lower need for carbon dioxide removal and the associated risks and logistics of this wide-scale use of this technology. In fact, the Remind Magpie model shows that requirement for carbon dioxide removal is extremely low, but even for the image model, it is lower than what we would see in the SSPs. And overall, we see that there is a higher energy and food security kind of built in, well, not built in, but resulting from these narratives. But one really take-home message that I want to stress is that concerted actions are required. Within these narratives, we've kind of taken a holistic view of building in these narratives into the model. And what we see, especially when contrasting to the SSP2, is that climate policy alone does not move the world closer to sustainability, does not reduce the trade-offs and increase synergies. In fact, it does the exact opposite. We saw that climate policy may increase food insecurity, may increase energy insecurity, and may increase certain other pressures and impacts. So concerted action across a number of domains is required to make these projections feasible. That's what I've prepared to do. Thank you very much for your attention.
Thank you very much, Vassilis. So we now first have asked speaker to directly comment on your presentation. And this is Roberto Schaeffer from Brazil, from the Institute called CLEW. Roberto, can you in a couple of minutes reflect on the presentation of Vassilis?
Yes. Hello, everyone. Thank you very much, Detlef. Thank you very much, Vassilis. Well, it's a great honor for me to be here. And let me start by saying that this project is really great. It's a great contribution to the field, and the results are also very interesting. Let's say, although not exactly unexpected, and I'm gonna explore this a little bit later. And the reason why I'm anticipating that the results are not exactly unexpected, because these SDPs, by design, you have done a couple of things that somehow, let's say, already predetermined what's gonna happen next. Also, I have to recognize, or we have to recognize, and this was mentioned before today, that the difficulty in translating the political 2030 agenda into targets and into analytic targets and into indicators. So this is, I know that it's a great effort to do that, and we have been fighting this for quite some time. So it's a big, let's say, merit of this project to be able to address these issues and somehow solve some of the problems we have been facing in our community. In fact, our community, the I am community, has been using these models mostly for mitigation, but we know that mitigation is not enough, or climate is not enough. Let's say, we know very much in this community about the planetary boundaries, and that we really have to go far beyond climate only. And that's why it's so important to add this multi-dimensionality of SDGs into the analysis. And this is the merit of this project. Also, in the case of the presentation by Vassilis, let's say the CLEW nexus is also critical for mitigation. And that's why it's so interesting, this result, and this is the beauty of this work here. Let me make a few more specific comments here, let's say, about these concepts of sustainable development pathway, the SDPs. Very interesting concept. Let's say we cannot find this in the literature. This is a very recent concept, so I think it's very interesting. The issue of the target seeking scenarios, also very interesting concept, which is very well used in this work here, and also the target space as presented here today. About the 3 SDPs, I think these are, in my view, the bad news. Let's say the most interesting results, in my view, at least in the case of the CLEW nexus, are for those SDPs that, in my view, are less likely. For me, unfortunately, the most likely SDP, if you can aim for one of these 3, is the economic-driven innovation SDP. I think this is the more likely one. But when you look at the CLEW results and even our other results of this project, let's say the synergies and the trade-offs are more modest, precisely in that scenario that I believe is the most likely. Although Gabriela has mentioned this today, that eventually different regions of the globe may go more for the EI or for the MC or for the RC. But in my view, it's more likely that, let's say, at a global level, the EI is more likely, and these have implications for the result of the project itself, and also for the results that Vassilis has shown. For example, if you look at the case of final energy demand, as Vassilis has indicated, let's say, the results are not that different in the case of the EI as compared to the SSP2 or SSP2 1.5. Mainly if you look into the medium term, like 2050. Really, the different SDPs, let's say, differentiate from each other much longer in time, 2075, 2100, by 2050, when probably we're gonna need to be net zero or something around that. These different SDPs are not that different from the SSP2 1.5. And again, mostly in the case of the EI. The same happens in the case of, let's say, agriculture demand, or in the case of primary energy. So we do not see that much difference, except for the longer term. By 2050, in my view, results are not different, and this is a pity, but this has nothing to do with the project, but basically this is a function of the results, so we have to accept that, unfortunately. My final comment here, let's say, all three SDPs put less pressure on CCS, as Vassilis says, so this is great. All SDPs show an increase in natural lands, which is also good. But again, here too, the more likely scenario, in my view, does not show so much difference in the case of natural lands. So in sum, my final comment here, the SDPs reduce trade-offs and increase synergy. This is great. But as I said before, mostly over time or mostly after 2050. Up to 2050, in my view, those results are not that different. And I think these are the bad news. Let's say, in order to deal with the issue of climate mitigation, in order to deal with the issue of the SDGs, up to 2050, probably we're going to see a lot of pressure, negative impacts on land, energy, et cetera, and only in the much longer term, the SDPs or the different SDPs show the benefits of going one way or the other way. That's from my side. Thank you very much.
Great. Thank you very much, Roberto. Maybe we can have one single question. In this case, on the web, Edgar Hertwich from the NTNU from Norway, who will present the work that we have done in SHAPE with respect to resource efficiency. So the floor is yours, Edgar.
All right, it's my pleasure to present this work.
Edgar, can you still make it present mode? Yeah. Okay.
Yeah, I'm just looking. Well, let me see. I guess I need to share and unshare. You share. This worked yesterday when I tried it, but okay, here we have it. Sorry.
Yes, perfect.
Start with the beginning. So the point of this work here is that we would like to look more at the issue of resource use and in particular the use of materials. This goes back to some work we have done earlier where we have found that while integrated assessment models have always modeled the demand for material, it was not coupled to the level of activity that happened in the material using sectors, primarily construction and industry. And this is something that we are trying to address now through this ongoing work. And we have previously done work that looked at housing, so the residential buildings, and at cars as both containers for materials and obviously as energy using activities itself, as it has been for quite some time. And in this project allowed us to basically look at the interaction of a more bottom-up modeling of the use of materials in the form of products, and the quantification of the material demand within specific products, and the larger modeling of the economy and the energy system as it happens in the integrated assessment models. And so basically, the modeling that we do in the industrial ecology models looks at the whole life cycle of identifiable products. This means that they are designed and manufactured. First, the materials are extracted, of course, and the products are designed and manufactured, and then they're used. And then at the end of the life of the product, the question is what happens to the materials. And the background for this is that nearly a quarter of greenhouse gas emissions are associated with the production of materials. And therefore, we reason that it is important to know, first of all, how much material is used in which activity, and second, to look at opportunities to reduce material use throughout the life cycle of products. And this figure here, the circle indicates basically what are the opportunities for reducing material use. And so we can design products that require less materials. We can use materials that require less or cause less emissions in their production. We can reduce the amount of waste that is associated with the production or manufacturing process. We can use the products more intensively through various technologies. We can extend the lifetime of the product, hence requiring fewer materials to replace existing products. We can recover the materials at the end of life and make sure that they are sorted correctly, or reuse components from the products directly. So there are various ways in which materials can be saved along the way. And some of these ways actually have implications for the energy demand, either positive or negative. And this is why we have models that address these product systems specifically, for example, building energy models or vehicle energy use models that we use in our work. Now, in the SHAPE project, to represent these three different scenarios, we actually identified specific material efficiency strategies with the storylines of the scenarios. So the economy-driven innovation scenario imagines a high-tech future. And so we have looked at these three options that we have affiliated with this EI scenario, using less material by design, fabrication yield improvements, and enhanced end-of-life recovery. For the RC resilient communities scenarios, this is about simpler living. So we have imagined that we use buildings more intensively. That means that we require less building space, as you have already seen in the previous presentation. And we require fewer cars because we share rides, more people in each car, and we extend the lifetime of cars once we have electrified the fleet. Which, as I said earlier, reduces the number of cars that we need to produce. In managing the commons, it's a more top-down approach that requires a lot of policy intervention. And so the idea is that we have car sharing as a strategy, and then we focus on the scrap diversions or more efficient recycling processes and the reuse of components as strategies. And so now we have modeled these through the ODIM-REC model and quantified the material demand. So I will show some charts that actually show the amount of material use in the different scenarios using the SSP2 scenario as a reference. And you can see in general that the SDPs have lower total material demand. So the sectors, again, that we have modeled here is the total building sector, also now also including non-residential buildings, which we did a fair amount of work on, and cars. And so, and you can see that the economic innovation and resilient community scenarios have lower material use than the managing the common scenario. So those strategies that are adopted in these scenarios are more effective. The total material demand can be split into primary materials and materials produced from raw materials, and secondary materials produced from waste via recycling. And the managing the commons has the largest recycling streams because it has a higher recovery of materials from the recycling, but also because it does have quite a high amount of materials that are required. So as you put more materials in, more materials come out at the end of life. And the resilient communities has a fairly low material demand on the primary production, but it also produces less materials because there's less materials that are in input to the entire process. So if we look at scrap from fabrication, so this is sort of the production waste, we can see that this is influenced both by the volume of total production and also by the amount of fabrication scrap per unit produced, which we assume to be low in the economic innovation scenario. And the material to landfill there is not that much interest, that much difference, and that was interesting for us. And it mainly reflects the very long lifetime of, so the highest volume of waste we get from demolishing buildings. And of course, the quantity of buildings that is demolished in 2060 depends on how much was built in 2010 and before. So for that sector, there is not that much impact in terms of landfill waste from the strategies. Not yet, it will come later, right? So, and there is differences, there are regional differences in terms of how these stocks develop. For the OECD, we see a slight decreases in stock for the EI and RC scenarios. So the economy innovation assumes that we need less material per unit product, and resilient communities assumes that we use fewer products. And whereas the managing the commons approach doesn't make so much difference compared to the SSP2. In Latin America, we see that the demand or the total material stock will increase in any of the scenarios. This is also true for the other regions that still have developing countries. And that is just a fact that there is still a high demand for both vehicles and buildings in these areas. But you clearly see the impact of the various strategies on the final amount of stock that we assume here. On the per capita basis, it is a somewhat similar pattern, where we in the OECD have a fairly constant level, whereas there is slight increases or larger increases depending on the level of development that still needs to happen in other regions of the world. So much to our work.
Mute. Thanks, Edgar. And so, like with Vassilis, we have also asked person to directly comment on Edgar's presentation. And in this case, it's Julia Okatz from SYSTEMIQ. And so, Julia, can I give you the floor to give a first response to the presentation of Edgar Hertwich?
Yes, pleasure. Good to be here. And really good to hear both presentations also, because just reading it is always different. I believe Edgar has invited me to comment because I use a lot of these findings, both with governmental actors, but also investor communities who are increasingly interested in this. So I would comment very much from that perspective of who uses this for what, and also a bit egoistically, how can I use this for what? And that compels me to say, that this is already really useful, and basically just giving my big thanks for further refining these findings and explaining that a bit, but also obviously I can't help but ask for further developments of making this even more usable, because I hope that will happen. So I mean, first of all, I think this approach of really being clear on the demand sides in general, so basically the whole approach to sustainable development pathways, sorry, one sec, that is becoming increasingly useful because the awareness rises, and then with a particularly focus on materials, and that deep dive also, we've just seen that the interest and awareness is really growing, both in the private, sort of progressive private sector, let's say, and the governmental actors. So I think that idea that, especially with this whole narrative around hard to abate sectors, that you really can't tackle that anymore just by production side measures, so aka energy transition measures, that is really taking hold, and therefore the demand for these insights is really growing, right? So we're getting a lot of questions in terms of how much could circular economy and heavy industry help us reduce heavy industry emissions. How is that also then beneficial with critical raw materials that we would otherwise need for that energy transition? How is that helpful for cost? Obviously, that's always a big question. And how can it be also beneficial maybe for new business models, economic opportunities, and resilience at large. And I guess specifically buildings and vehicles, which now in Edgar and Co's model is really the focus. Almost absurdly, that has been really overlooked before. So when you look at this whole discussion around circular economy, which is really where this sort of material view comes from, it's a lot about textiles and plastics and packaging and so on. That's kind of how that theme came up, at least in Europe. Which is obviously important too, but then when you make the link to climate, obviously it's cement and steel, and then also biomass, that really is the name of the game. And I can't really say why that is still a blind spot, but it is. So I think these types of insight really make a difference. And I also wanted to say something that is probably rather basic, but in terms of value add, so these scenarios are obviously highly interesting and help, but even just the baseline, or even just the today, so the really detailed show of the stock, what is actually happening today and how is that interacting, energy demand, how does that interact with material demand, and for example in buildings, what is actually the material composition of these different building types, even thus just that is already really helpful. I've done a bit of research and couldn't really find anything else there. So maybe just to underline that. And now in terms of what make this even more usable, in case you can secure another big research grant and to continue this work, which I really hope. So I think one big thing is I guess the question around what and how this relates to realities, right? So these different scenarios of what if we did technological innovations, or what if we did really new lifestyles and so on. And those are all fascinating what if scenarios. But of course, when we work on this with decision makers, they want to know how this relates to what they're already doing, right? So the more I think we can relate this to actual realities and say, basically, here's what we see is currently happening in the NDCs, or this is sort of the reality that would come if we followed you know, what was just announced in the last Davos meeting. I don't know, whatever you want to make the link. I know, like, taking specific country policies can be politically difficult, but that's of course in the end the most useful, to say this is your current path, right? You're currently completely overlooking XYZ. You're just doing this, and this would be the outcome. And then also being even clearer about how that really hits a wall, right? So I see we have all these, Vassilis, I really liked how you explained all these trade-offs, and I love the graph on the, you know, on the land requirements and so on. I guess critical materials would be another really interesting one to see as like a really hard limitation. But still, I think most policymakers, when they look at these different scenarios, they think, okay, one will probably be more costly than the other. Yes, maybe one has more trade-offs, but effectively I can just choose freely from these, which is not true, right? It's like half of these are effectively not possible because, well, there's just not enough land, right? So it's not really just a trade-off, it's a hard limitation. So I think that would be worth making, you know, even clearer, to say that really in the end you only have the choice between two of these, or maybe this. And then the other one is, I guess, like the optimization one. And here I could come back to the materials, for example, right? So again, different scenarios is very interesting, but in the end, most people need to optimize for a clear objective. So they need to say, okay, we need to, you know, get this done in a certain time frame, within a certain cost frame, and within a certain level of rare material imports or something like that, right? So which of these scenarios would actually get me sort of closest there? And I know, you know, you have to explore these different scenarios, but most people just want to see sort of the one or two that actually gets them to what they need to get to. And I guess I could say many more things, but I have the suspicion I'm running out of time. So I will say one last thing, which is the where. So, you know, that most policymakers and also investors think in sectors and actors. So currently, for example, with the material efficiencies, you see, and then also the emissions benefits, these span different actors, right? Some of these really occur within like a building sector. The other ones really occur more like sort of in the heavy industry field, like the recycling and so on has to be done in that sectors. So if, you know, at any point we could together, or you would split this up, sort of, these are the actions that fall under the different types of actors, and these are the deductions really that would sort of occur under a heavy industry portfolio versus under buildings portfolio and so on. That is usually also a lens that would makes it more usable for especially policy actors that, well, for better or worse, you know, work in their ministries. I will stop there. Edgar, do you want me to say something else?
Edgar, any direct response?
Yeah, thank you, Julia. I think it is really important what you're saying, that it is important to identify where are the leverage points and who are the actors that can act, and how large are the leverage points. And, you know, I hope that the figures made it clear. It wasn't quite explicit, but most of the material demand is in developing countries. And this is really a difference from the energy demand. Most of the energy demand is still, or a large fraction of the energy demand is still in rich countries, right? And so a lot more opportunities for material efficiency actually arise in these countries where we hope for rapid development, or we are experiencing rapid development. If you look at cement production numbers, China produced 2.5 gigatons of cement last year. In the US, it's 0.09 gigatons, right? So this is the two largest economies in the world, just a drastic difference. And why are we using so many materials? And I think that the material use gets really ingrained in our ways, in our economic structures. I can say that for Norway, we have very generous subsidies for home ownership. And it pays for wealthy people. If you get a pay rise, you move to a larger flat because you can save taxes that way. If I look at China, go back there, home construction and any way of construction is the way they keep their economy going. So every time there is an economic crisis, the government stimulates construction, right? And so that's why they can't get away from it. If you look at the numbers, you know, you living in London are very cramped compared to people living in Chinese large cities today, where you know, average floor space per capita is around 40 square meters. So very much at the European level. And still there is this large construction activity, and it is a paradox. But the economy has been set up that way, and it is very hard to actually achieve the structural change that is necessary to shift to a different type of economic activity.
Yeah, maybe one quick response as well to the last part of your response, Julia, where you were talking about the implications for policymakers and where are the intervention options. The last section of today on governance is also going to address that as far as we could do this in this project. But I think that indeed it's an important area to further develop these scenarios. Anyone else that still would like to